Hello and welcome to the podcast Spacetime Fika. This is a new podcast about physics and astronomy created by me, Jonas Enander. I have a PhD in physics and I currently work as a science communicator in Stockholm, Sweden. And Sweden is also my home country, which is reflected in the name Spacetime Fika. The first word, spacetime, stems from Einstein's theory of relativity, whereas the second word, fika, is a Swedish word about a very central activity in Sweden, namely to have a social coffee break, a fika, together. And the goal of this podcast is to meet people from the world of science and discuss in an informal way, like having a fika, a coffee break, what we know about the universe and how we have figured that out. In the first episode, we meet Salvatore Vitale in his office at the Massachusetts Institute of Technology, also known as MIT. Salvatore is Associate Professor of Physics and a key member of LIGO, an observatory that searches for signals from colliding black holes and neutron stars. This is known as gravitational wave astronomy, and it's a field that is growing rapidly today, giving us new insights into not only black holes and neutron stars, but also things like the expansion of the universe. Salvatore is the perfect person to tell us about this exciting science, and we recorded this episode last year, right before LIGO started its fourth observation run. So, without further delay, here's the first episode of Spacetime Fika. I hope you enjoy it. Okay, welcome to this episode, Salvatore Vitale. So we are going to talk about one of the most exciting science experiments I think has ever been made, which is the hunt for the gravitational waves emitted from merging black holes and neutron stars. So welcome to this episode.
Thank you.
And we will talk about the history of this discovery, which was awarded with the Nobel Prize in 2017. And we will also talk about the current state of knowledge, what have we learned from the experiments that have been made. And we will also talk about the future a bit, what is on the horizon in terms of the study of black holes. But we're going to start to talk about you first and how you got started in this very exciting field. So can you tell a little bit about your background and how you got into physics?
Yeah, so I always liked science and physics since when I was a kid, pretty much. And so I did my undergrad in Italy in physics, naturally. And then I always liked theoretical physics more than experimental one. And then, anyhow, so for my PhD, eventually I went to Paris and did some work on relativity and gravity, but it was really purely on the theoretical side for the first 18 months, something like this. And then just randomly, accidentally, at a conference that my thesis advisor was co-organizing in Paris. And as a student, of course, I helped, giving people their badges, telling them where to go. I just saw this person that, was trying to connect his internet to the Wi-Fi and tried to help. I failed, by the way. Yeah, but we started chatting, and it turns out that this person was a professor of physics in Arizona, working on LIGO, and so it was chatting and talking about the common interest. He was kind enough to tell me that he had actually some funding that he could use. So he asked me if I was interested in spending a couple of months in Arizona to work on LIGO. Related research topics, and then I said, of course, I've never been to the US, sounds great. And so that's how really my research shifted from like generic theory of gravity to more gravitational wave science. And then from there I went...
Wait, hold on. So
yeah.
That shift happened, which in the end led you to, your entire career, because you were trying to help this professor.
Totally. So I owe a lot of what I'm doing to Ubuntu not being able to connect to the Wi-Fi, Linux, 10 and some years ago. Absolutely. Sometimes life is like this. There are, random events that move you in a different direction. And anyhow, and so this was, so I finished my PhD in 2010. Then I did a postdoc for 2 years in Amsterdam, still like on gravitational wave research. So I shifted more and more from pure theory to analysis of the data, pretty much. And then I came to MIT in 2012, first as a postdoc, researcher, and then for like 1 short year as a research scientist, and then as professor in 2017.
Yeah, we are sitting here in your office at MIT right now, and I see on a wall here, you have a photo. It says, it's a group of people. You're one of the group and one of the members in this group, and it says Stockholm, December 9th, 2017. Can you describe to the listeners, what are we seeing on this photo?
Yeah. So as you mentioned, gravitational waves have been one of the probably most impactful new lines of research over the last few years. And as part of that, our first discovery in 2015 was awarded the Nobel Prize for physics to Ray Weiss, Kip Thorne, and Barry Barish, who are among the people who like really started the field in the 70s. In particular, Ray Weiss here at MIT, was one of the pioneering figures, right? And so Ray was kind enough to reinvest some of the money of the prize to invite a few people here at MIT and outside of MIT to go to Stockholm. And so that's when that picture was taken. This was basically the night before, if I remember, the actual ceremony with the king. We did not get to go to that one because even Nobel laureates have very few tickets. So once you give it to family, the president of MIT, whatever, there are not very many left. And but so we had our own party even that day. But the night before, so we had our party with the Nobel laureates, and there you see the president of MIT and Nergis Mavalvala, who is now the dean of science of MIT, and she's a LIGO, faculty, and other faculty research scientists here at MIT. So it was great. It was pretty great.
Fantastic. So we are going to go through now what actually happened that led to this Nobel Prize. I mean, the actual science behind it. But before we do that, I just want to ask, since I'm from Stockholm, what did you think about Stockholm?
So I love the place, and I love the food too. Like,
oh, really?
I ate a huge amount of salmon for from breakfast on, and no, I don't eat fish anymore. But back then I did, and it was great. I really enjoyed the city. It's really a beautiful city. I only spent 3 days or something like this, so not a huge amount of time. And I went, of course, to the Nobel Museum, and I cannot remember the name, forgive me, but you will know. I went to the museum where they have a massive Viking boat, pretty much.
Yeah, the Vasa Museum. Yeah.
And it was beautiful too. Yeah. So it was really an enjoyable time and visit.
I've never been to that Vasa Museum.
Okay, you should. Then you should. It's really great.
I'll take your advice. Okay, 3 days in Stockholm, eating copious amounts of salmon. It sounds great. Okay, but let's go back now a little bit to the topic of today's talk, which are merging black holes and gravitational waves. So we're going to start with gravitational waves. So what can you describe? What are they?
Right. So the way I think about it, it's not too dissimilar from electromagnetic waves, which are light, right? Which, of course, we experience daily in our life continuously. And so the same way, if you take an electric charge and you shake it, it's going to emit light or X-ray or gamma ray, depending on the frequency. If you take a mass and you shake it, it will emit also waves. And those are called gravitational waves, right? The main difference, as probably we're going to discuss later, is that it's much harder to produce gravitational waves. So while I can produce electromagnetic waves just in my office with a radio, right, or an emitter or a microphone, to produce a significant quantity of gravitational waves, I would need an incredibly large amount of mass in a small volume, so something very dense. That is the main difference. But everything else is the same. They are produced when you accelerate something, either mass or charge, and then they just travel at the speed of light. And, if you know how, you can reveal their presence and try to learn something about the source.
But when we talk about electromagnetic waves, those are, well, as the name suggests, waves in an electromagnetic field. So, and usually when we think about waves, let's say ocean waves, those are waves in the water. But what are gravitational waves actually waves of?
That is it's a fantastic question, even from an historical perspective. So the gravitational waves are waves that propagate in the fabric of space-time. So what is wiggling is actually space-time itself, right? Which of course is not incredibly easy to visualize, right? But probably the most common way of thinking about it is that you can think of space-time as a flat surface, like the surface of your bed. When you're not in bed, right, it's just flat and there is nothing there. And then if you put a bowling ball, it will make like a big dip, right? And that would be a static thing. If you just put a bowling ball in your bed, or a cat, there will be a small dent in the bed, but it doesn't move, it just stays there. So gravitational waves are kind of the same thing, but now the disturbance relative to the flat surface is not localized and constant and always the same like a bowling ball, but it's like if you're jumping in bed and then you're making these waves basically going away from where you're jumping. And I think that's the best way I can really explain, because then we get in the realm of relativity, which is not incredibly trivial to visualize. But really, because we are all embedded in space-time, what is really happening if you are introducing perturbation in space-time, which is what gravitational waves are doing really, is that you are modifying the distance between objects embedded in space-time.
And it's easy maybe to imagine the space aspect in the way you describe it, with a sheet that is changing.
Yeah.
But the time aspect, so there's a wave in time as well?
Yeah, so I think that is a bit harder to visualize, and it leads to, it's a source of confusion historically, right? So I think probably for the purposes especially of explaining how LIGO works, it is best to focus on the space aspect, because that's also how LIGO measure things, right? You try to measure the distance between two objects and see if it changes. But yes, it is, you're right, like relativity and general relativity treats space and times simultaneously, such that if you perturb space-time, you are also affecting time. Then, of course, it's not necessarily a perturbation at the same level of magnitude. One may be bigger than the other, but formally you are affecting both space and time, yes.
And that really is one of the aspects, as you say, that's kind of hard to wrap the head around, and also shows why it probably took a long time to figure out exactly how this works. So, as you said then, that this one aspect is the detection of these gravitational waves, and the other one is the creation of these gravitational waves. So before we move into the detection aspect, which is, super fascinating how it's even possible to detect them, let's talk a bit about how they are created first, and then we'll see how they are detected. So, because you said you need a huge amount of mass compressed in a very small region of space, and then I start to think about, that sounds like a black hole.
It does smell like a black hole, right? And in fact, it is a black hole. So let's see. So first of all, the main reason why, if I just move my hands and not producing gravitational waves that LIGO or the detectors or Virgo can detect.
Yeah. And for the listener, Salvatore is moving his hand very rapidly right now.
It's because, so as I said, gravitational waves are perturbation in the fabric of space-time, but it turns out that space-time is very stiff, So it's not like one of these nice water mattresses that they just, are very soft and you lie down and you very easily sink in. They are like a very, very hard, old mattress from your grandparents, right? Made in wood or something very hard, right? And so what that means is that it really takes a lot to, to bother it, right? And so, of course, I'm making a complicated mathematical story very simple. But what that means is that you really need to put a lot of stuff in a small volume, okay? And now, if we think about what are the known objects in the universe that fit that description of a lot of mass in a small volumes, then we are thinking about the densest object in the universe. And those would be white dwarfs, or neutron stars, or black holes, and all of these are the end product of the life of stars after they go supernovae, right? And those are exactly, at least neutron stars and black holes, not white dwarfs, the type of sources that LIGO and Virgo have seen up to date. And so I should also say that to produce gravitational waves, you need motion, and in particular, you need acceleration. So if I just take a black hole and it sits somewhere by itself, it's not going to produce gravitational waves. It needs to be accelerating, and for example, in a binary system with another black hole or neutron stars. And again, I'll stop here because probably going to talk more about that specifically, but these are exactly the type of sources we're seeing right now.
Right. So you say that there's not enough to have just one black hole.
Yeah.
So we need two, for example.
Yes.
So can you explain what happens then when two black holes meet and emit these gravitational waves?
Right, absolutely. So what happens is the following. The type of system we have on mind, first, for simplicity, is like a binary, like the moon and the Earth, but both of these objects are black holes, right? So they are rotating around the common center of mass. Now, as they move around one another, they emit gravitational waves. But gravitational waves are bringing energy away from the system, right? They're removing energy, right? Just like light warms your skin, right? Because it's carrying energy. Gravitational waves also carry energy. But if you're removing energy from the system in relativity, it turns out that the two objects have to get a bit closer. But that's a runaway process, because closer means that you're emitting even more gravitational waves. So what is happening is that a bit at the time, these two black holes are going to get closer and closer and closer as they are emitting more and more gravitational waves. And you guessed it, eventually they will just smash against one another half of the speed of light or something like that.
Yeah, it's amazing. And that's when you emit these copious amounts of gravitational waves that we are hoping to detect here on Earth.
Right.
And have detected.
Right, we have. So I should say also, just for clarity, gravitational waves are emitted throughout this whole process, not just in the last few seconds. What changes is the energy, how much energy you have in a specific amount of time, so the power, and at which frequency the emission happen. Because when the two objects are still at the beginning, so rather far, these gravitational waves are at a frequency where LIGO and Virgo cannot see them. They're just too low frequency. And it's really in the last few hundreds or thousands of orbits that they are at the speed of a kitchen blender, pretty much. So a few hundred times rotation per second. That's the sweet spot for the detectors we have today.
A kitchen blender.
Pretty much, yeah. Kitchen blender, yeah.
Okay, so then let's move back. We're going to return to this question of what happens when they collide and so on, because there was some very interesting detections being made there. But let's go back to Earth now and see how we actually can detect this, because it just, as you say, the effect of this to disturb space-time is very, very difficult to do. Mm-hmm. And at the same time, when the waves come here, they are induce a very, very small perturbation here on Earth. So what is required to measure them?
Right. Okay, so let's go in order, which and I'm going to spend maybe some time on this because I think it's one of the most fascinating, really, part of the history of relativity, is that at the beginning, meaning for the first few decades after Einstein proposed relativity, and he figured out that gravitational waves were a consequence of his theory, it was not even obvious whether it was a real thing that you would ever see versus a fluke of the math. And the reason why I say this is because it's a bit technical, so feel free to cut this later. It turns out that you can describe Einstein relativity in any system of coordinates that you want, but somehow things look slightly different. So there are things that are always the same, and those are the physics. But the description of the physics depends a bit, right? For example, earlier we talked about is only space or both space and time affected by gravitational wave or gravity, right? The answer to that depends on which coordinate you use, right? And anyhow, long story short, it took actually people decades until the 70s, if I'm not wrong, to finally convince themselves that gravitational waves were not something that you can just cancel by changing coordinates, but they have a physical effect, right? And what the physical effect is that if you have in a region of space-time, like my office here, two masses which are falling under gravity, in this case, by falling, we really mean suspended like pendulum, okay? Suppose they are initially at some distance, like a meter, whatever. If a gravitational wave passes by, what it does to space, in the coordinates I'm using, is that it stretches space in one direction and squeezes space in the orthogonal direction. So what the distance between these two mirrors or these two masses would do as gravitational wave passes by is to change in a particular way that Einstein taught us how to calculate, 100 and some years ago. So theoretically, what you have to do if you want to collect your Nobel Prize, it's very, very simple. You just have to monitor the distance between two objects here at Earth very precisely and show that it changes in a way that is predicted by Einstein. Now, what is the catch? The catch is that the amount by which they move is offensively small. Maybe we're going to talk more about LIGO later specifically, or Virgo, but just to give you an idea, if you place these two objects that you're monitoring the distance of 4 kilometers one from the other, a typical gravitational waves like the ones we are seeing today would change the distance between these two objects 4 kilometers apart by less than the size of a proton of one nucleus, which is, of course,
it's crazy.
Yeah, it is crazy, right? And that's why it took, many decades, and that's one of the reasons why a Nobel Prize was awarded, is because he's not only a scientific, but he's also an incredible technological challenge to make a measurement which is this precise.
Yeah, and what I find really fascinating about this is what you just said was that it first took several decades just to figure out the mathematics. I mean, that's almost 50, 60 years after Einstein formulated general relativity. And then it took another 40, 50 years to actually make the measurement and detect this.
Absolutely. Yeah. I mean, Ray Weiss had the idea, among others, to use lasers originally in the 60s/70s. So it's a long time ago. Most of the intervening time went into being sure of the source of noise were under control, and you could build masses, and for masses we use mirrors which are polished enough, and that you can remove the source of other things that can make your masses move, right? Right now, you and I are talking, and even though we don't notice it, we are ever so slightly shaking just because everything shakes around us, right? Because of, the Earth is shaking a bit. And for us, it's not a problem. But if you are trying to measure the distance between two objects to the size of an atom or less, then every small amount that these things move for reasons which are not astrophysical, then that matters, right? You need to better be sure that you understand all of these things and you can remove as many of them as possible. And that's incredibly challenging.
Yeah, so let's talk about this. So suppose you say then that we need two masses, we need to monitor the distance, how it changes between them, because since gravitational wave is a space-time disturbance, then distances will change, and that's what we need to figure out how they change. So how do you go about then in practice? Because you mentioned lasers, suspended mirrors, we have two sites. Let's talk about LIGO now. And
absolutely.
Begin with, yes, what does LIGO mean?
Right, okay, so LIGO is, as I should say, there are right now 4 operating detectors in the world of kilometers or larger. There is the 2 LIGOs in the US, and LIGO stands for Laser Interferometry Gravitational Observatory. Then there is Virgo in Italy and Kagra in Japan. And so the way they work, it's really pretty simple conceptually, right? If you want to measure the distance, say, between you and an object, these days it's very easy to go on Amazon and buy a laser gun that basically sends some light to the object. The light bounces back to the gun, and you measure how long it took, pretty much, and you divide by 2, do some mathematics, and you get the distance. And so that's exactly the idea, when you really boil it down to the very minimum, of gravitational wave observatories. You just measure the distance between 2 pairs of mirrors arranged to form an L letter. And the way you measure the distance is to send a laser beam, right? And basically just count how long it takes for light to go in the 2 directions, okay? And I'm making it very, very simple. Of course, it's much more complicated than this. And so what you can do then is say, okay, I can build my detector such that when there are no gravitational waves, say the travel time of the laser in the 2 perpendicular directions is, say, identical, right? But now as gravitational wave passes by, the horizontal distance will change in a different way than the vertical distance, so I will have a differential change. And that's exactly one of the great things that lasers are good at doing, is to measure small variation in the path that light follows across different directions. So that's the working principle of LIGO. Now, as an historical, pretty entertaining fact, this way of measuring things is called interferometry, because light interferes, and it's particularly, I think, interesting and fun that the idea of interferometry was actually introduced in the second part of the 1800s by, among others, by Michelson and Murray, which used it to try to explain if and how the speed of light would depend on which reference frame, and they failed. They actually won a Nobel Prize. And that is what eventually led to Einstein's original special relativity and then to general relativity. So I find this particularly nice that there is this loop that we're using the same idea that they used 150 years ago to, pioneering what eventually will lead to actually understanding how light and gravity work.
Yeah, definitely. And we also have the interferometric experiments done by the Event Horizon telescope with very long baseline.
Of course.
So interferometry is really there at the heart of this black hole research.
I use that very often when I teach relativity to my student, when I go to the Michelson-Morley, because I told them, this literally was a failed experiment. They did this to show that the speed of light changes, and they found that it doesn't change. So by the look of it, they failed, right? But I think some people call this the most successful failed experiment in the history of physics, because by doing so, they actually found something more important.
It's very fascinating. But LIGO didn't fail. It was possible to see the change in the distance between these L-shaped lengths. But as you mentioned before, it required really good knowledge of all the types of changes that are also introduced by effects here on Earth. So, and that's something I find really fascinating. It's also the same with the Event Horizon telescope experiments. They need to have really good control of where the telescopes are placed on Earth. So they need to know continental drift and so on to do these experiments. Can you just mention again some of the difficulties?
Absolutely. And that also reminds me, I didn't answer the second part of your question, why we have more than one LIGO or Virgo. Right. So it turns out that there are a lot of things that wiggle around us, right? And they make a source of noise. And so for us to be sure that what we saw comes from the sky, as opposed to something else, of course, we need to make a convincing case that is not due to the FedEx truck, right? That just went into the bumper a bit too fast, or something like that. And so some of the sources of noise are just always there, like seismic noise, okay? Just because the Earth vibrates a bit at low frequency, right? Some, which are also always there, are due to quantum mechanics. Say, we use laser to do this measurement, as I mentioned, and quantum mechanics tells us that we can think of lasers as being made of a lot of particles called photons, but it also tells us that we cannot know exactly the number of photons in the beam. That's just Heisenberg Heisenberg uncertainty pretty much. And so that uncertainty is a source of noise that we also have. And those are always there, and we know how to calculate them. Then on top of that, there are transient source of noise, like the example I made is not a random example. If you have a car, these things are so sensitive that if you have a car or an airplane, flying above, just the vibration in the air introduced or in the surface, in the ground, will give you a measurable effect. I think a famous history, I think in LIGO Hanford, so you can ask when you go there, of a mysterious source of noise that they were seeing at some point was due to a microwave. That was a microwave that was somehow like producing glitches in the power outlet, and those, because everything shares the power, right, were somehow like converted into the gravitational wave detectors. So really these things happen, and that's one of the reasons why it's paramount, especially for the first discovery, to have more than one of these machines, right? Because now what is the key? If I have my power outlet going bad because of the microwave, it's very unlikely that that will happen at the same time in Washington State and in Louisiana and in Europe, say, right? While if you have a real gravitational waves coming from the sky, you should see it in all of the detectors which are part of your network in the same way, right? So the power maybe is more or less different depending on the position of the sky, but the shape should be like the same. You should see the same thing, right? So that's one of the reasons why we're having a network as opposed to a single detector, is really to convince ourselves that what we see is astrophysical. The other very important reason, and we're going to talk about this later, I think, since it's very exciting, is that a single detector at the time, one of these interferometers, cannot really tell you where in the sky the gravitational waves came from, or very poorly. So you need to have two to start learning something, or ideally three detectors, far apart from one another. And then you do basically time triangulation. It's like our ears work, right? And so that's one of the main reasons to have more than just one side, is to be able to tell our friends who own telescopes, hey, look there, because a gravitational wave just came from there. So you should really look that there is also going to be some light maybe coming from there.
So let's dive now into the science that has been produced by these amazing experiments. So the first detection was in 2015 then with LIGO, and that was presented then to the general public in 2016, and the Nobel Prize was awarded immediately the next year because it was such a huge discovery. So that was one detection. And then there were upgrades, and we are sitting here now because, as you mentioned, next week I will go to LIGO Hanford. This is a trip I'm doing in the US, and they will start the fourth observation run, where observation run is the major upgrades that has happened. So can we talk a bit now about going from the first detection to the situation today? How many detections have you made, and what have you learned?
Absolutely. All right. So as you said, the first gravitational wave hits us here on Earth on September of 2015, and I have a lot of fond memory and stories that I can share later if you're curious. And that, of course, was an incredible moment. You also mentioned that the actual publication happened in February of 2016, so that's many months after. Now, most of that time actually did not go into analyzing the data, because really, we had the tools. Of course, we improved some things during that time, but more or less like a few hours after that happened, I could have told you what was the mass of the two black holes and so on and so forth. Most of that time really went into convincing ourselves that what we saw was real, right? Because as you can imagine, we were well aware of the impact for science, right, of that particular claim, and it was incredibly loud and clear. It was like suspiciously good, right? And so we wanted really to check that there was nothing else going on, and that took a lot of time, right? And
I have heard mentions that someone maybe injected a fake signal.
Yes, so that's one of the reasons. Basically, what happened is that in the initial version of LIGO that ran until 2010, and Virgo too, we had a system to perform what we call hardware injection, which basically means that instead of waiting for a gravitational wave from the sky to move our mirrors a bit, we poke the mirrors, not with our hands. We use like coils. And the reason is that you can basically that way mimic a gravitational wave, and you can check that your algorithms work the way they're supposed to work. Basically, you see if you can find it, right? It's a way of testing your codes. And that's fine. But where it starts getting a bit more exciting is that in the past, before 2010, we also had the mechanism and the prerogative of doing that wiggle ourselves without telling anyone. So the only people who know are basically the directors of the three sites, LIGO and Virgo. That was called a blind injection because we didn't know. And one of these happened in 2010. It's called the Big Dog because the source was on the Big Dog constellation of the sky, and we found it, whatever. And so, of course, on September of 2015, when we saw this like incredibly loud signal, I mean, I can tell you, you can cut this later if you want. So I was in Italy just visiting my family, and just because of time zone and my expertise, I was actually one of the first people who could analyze the source characterization code, and this thing was like so screaming loud. And I clearly remember, an hour later, it was in the morning in Europe, my friends in the UK starts waking up, and I remember commenting with them on Skype, saying they really could have put some more effort in making it look more real. That is so obviously fake, right? It's so loud, right? They really didn't try very hard. And then a few hours later, people in the US started waking up and said, no, we have not done this, at least not intentionally, right? So a lot of the time later, the last few weeks and months, were spent into checking that, maybe the system didn't trigger unwillingly, or someone made a mistake, or whatever, right? A bug, you never know. And I mean, we can go into the really incredibly detailed level of testing that was done and eventually exclude everything. To give you an idea of how paranoid we have been, we even considered the possibility of a malicious attack, of someone in purpose doing this for some reason, right? And I think the conclusion was, someone said this in one of our calls, I'm quoting something along the line of, if someone really has done this, we should hire them because, they're better than us, because we cannot do it, right? And so it was really, an extreme level of vetting, again, because the stakes were very important. Now, that was the first one. Of course, it was exciting. But now, if you ask me, and many others in the world, in the collaboration, to me, that it's the beginning, right? That's switching the light from off to on, right? I've seen it. Now what? Okay, and we're going to talk about that later. But before we go there, so let me just mention that in the years following 2015, we have detected way more events and of different types. Right now, we have, depending on how you count, so how conservative you want to be in, am I sure it's astrophysical, or it could be possibly be something else? The ones that we're basically 100% sure they are astrophysical, they are 69 binary black holes, so one black hole banging with another black hole, merging together. And then we have two neutron stars with another neutron star, of which we are very sure, and two mergers of a neutron star with a black hole, so heterogeneous systems. And then we have a few more, and that's why the exact numbers changes a bit depending on what you're reading, that are a bit more marginal. So they may be real, but we're not that sure.
Yeah, so let's talk about that, because you can really start to do some demographics now of this black hole population.
Absolutely.
And as you mentioned in the beginning, what you are dealing with here are black holes that are formed from, or maybe are formed, we should say, from the collapse of stars. You mentioned neutron stars, white dwarfs, and so on. But when you start to map out the masses of these black holes, what do you see? What's your conclusion? And could you just tell also before that when you get a signal, what is the physics you can extract from this signal?
Absolutely. Yeah. Okay. Those are all fantastic questions. So let's start from the end. So gravitational waves do encode the properties of the sources that they are produced. I mean, it's just written there. It may be very hard to read, but it's somewhere in those wiggles, right? And now the main things we can hope to extract from the data, if we're thinking about two, say, objects like neutron stars and black hole colliding together are the masses of those two objects. Like typically we quote them in units of the mass of our sun, so like 10 solar masses, 5 solar masses, something like that. And then the angular momentum, like the Earth and the Sun rotates around their own axis, black holes and neutron stars are expected to do the same thing, right? And then also other properties of the binary, such as where is in the sky, what is the distance from us, how is the orbital plane oriented relative to us, when did it emerge, and so on and so forth, right? So these things are all written then. Now, the fact that they are all encoded does not mean that they are all equally easy to extract. For example, it's much easier for us to measure the masses of the two compact objects, like black hole and neutron stars, rather than the angular momentum. It's just because it's physically easier to read from the data. And so then going back to what we have learned, it's maybe not surprising that one probably of the most important things that we have learned is about the masses of these black holes, just because we're better at measuring them. Now, before I tell you what we have learned, let me tell you, because it's going to be relevant, what we knew before LIGO and Virgo, because the truth is that astronomers have observed black holes for the last few decades, right? Using radio telescopes and X-ray telescopes, right? And with photons, so with light, we have learned that black holes exist, first of all, which was not always obvious, right? And we have learned that there are black holes of masses from in our galaxy from around 7, 8, 10 times the mass of our sun to maybe 20, something like that, somewhere in that range.
Okay. And now we are excluding the supermassive black holes.
Yes, of course.
So yes.
Then that's an important point. And then what astronomers have found is that somehow surprisingly, there seemed to be a big gap after 20 solar masses. Nothing, and then you restart having black holes again at around 1 million solar masses, and you go up to 1 billion solar masses. Those are the black holes at the center of the galaxy. And in fact, it's one of the open questions of astrophysics. Is there anything in between? If not, why? Do we understand it well? And so what I tell you then makes it, I think, clear that it was a big surprise when LIGO comes online, first discovery of gravitational waves, two black holes. They are both roughly 30 solar masses, which is much heavier than what astronomers have found before. And now, fast forward in 2023, we have, as I mentioned, 69 binary black holes. So we have measured their mass distribution, and we have found that is not uniform, is not equally likely to find black holes at any given mass. It's easiest to apparently find black holes in binaries at roughly 10 solar masses. And then as you increase the mass, you find fewer and fewer. So if you think of a line that tells you how many you have, it is very big at 10 solar masses. Then as you increase the mass, it goes low and low and low until you reach 30 solar masses. And then somehow there is a bump at 30 solar masses. It goes up again a bit, and then it keeps going down, and it tapers off at around 60, 70. Is very uncertain at that level. And so what that teaches us is a few things. Some that makes a lot of sense and are very easy to explain. For example, why it's easier to have lighter black hole than very heavy black hole? Well, that is probably because if black holes come from stars, it makes sense because stars are also much more numerous when they're light than when they're heavy, right? And so if black holes from stars, and there are fewer very massive stars, then there should also be fewer very massive black holes. Reasonable, it makes sense, right? The things that are still worth investigating, that are an object of intense research, are a few. I mentioned this bump at 30 solar masses. We currently do not know for sure what that is due to, right? There are theories, there are many theories, but there is not an agreed upon answer. So it's something that over the next few years as we get to measure this feature better and better with more sources, will not be more. The other one is exactly where does that curve goes to zero, like as at 80, 70, 90, 100, or they just get very rare, but they're still there. We just don't have enough detection yet to know. And that's an important question, though, because one of the most important, probably open problems of astrophysics is that nobody is sure how the supermassive black holes at the center of the galaxies formed very, very early in the history of the universe. One of the theories that maybe they formed by merging smaller black holes over and over and over and over. But if you do the math, you show that to do so in a way that produces supermassive black hole early enough in the history of the universe, as early as we find them, you need to start from black holes which cannot be 10 solar masses. They have to be bigger, hundreds, thousands, right? Nobody really knows. And so if those black holes are out there, we should see them. Maybe we should see them, right? And then finally, the last interesting thing about this mass distribution is that I said he has a peak at 10 solar masses, roughly, and then even on the low end, it goes to lower and lower again. So we did not find black holes of 3, 2, 5, right? Or very, very few. And so there are theories as for why this may be expected due to stellar and binary evolution. But to me, these thinking about the mass, these are the most exciting area of intense understanding in the observing run that you mentioned starts in a couple of weeks, because we're going to get between 2 and 400 binary black holes, depending on exactly the sensitivity of the detectors. So all of these things, which right now are pretty uncertain, I mean, we are sure they're out there, but we cannot really measure them to percent level yet. They will get much, much more precisely measured. Maybe the last thing I will say, then I drink some tea, is spins. So we can say something about the angular momentum of these black holes, because again, it's written on the gravitational waves. What we have found is that our black holes seems to be rotating around their own axis very slowly. And in relativity, we typically measure this rotation speed with a number from 0 to 1. 0 means you are not rotating. 1 is like 100%. You're rotating as fast as you can. And our sources, our black hole seems to have this number to be around 20%, 15, 20%. So it's very low. And it's a bit puzzling, because if you ask what is the same number for the black holes that astronomers have found with telescopes, well, then you can get anything from 0 to 1. They found a few slow one, but also a few very fast one. Okay, and so there is also already been, and there will be even more research in trying to understand what is this difference due to. Is this because our black holes are formed in a different way, or have they evolved in a different way, or what else is going on?
Okay, that's great. But to me, it seems a bit unclear. Can you say with 100% confidence that the black holes that you have observed actually come from the collapse of stars?
Well, I cannot say anything with 100% confidence, even when I'm going to have for dinner tonight. So, it is very likely because we understand the life of stars, and we know how they end their life, right? We have seen supernovae and so on and so forth. And so it's very well established that black holes are left over from the life of massive star. So why I'm not saying I'm 100% sure? Because at least theoretically, there are alternatives. There are two main alternatives I can mention. One, it's so-called primordial black holes. So those would be black holes which are not formed by a star when it dies, but they're basically formed shortly after the Big Bang, just because there is so much stuff that it collapses gravitationally in clumps, roughly speaking, right? And those have been theorized in the 70s, if I'm not wrong. Now, why it's less likely? Because you can do the math and you can show that these primordial black holes would by now mostly have already merged. Okay, and so you should expect to find most of them early in the history of the universe, not today. The other possibility, which is not quite black holes, is that there may be some other object out there which look a bit like black holes, but they're not quite black holes. Those are typically called black hole mimickers because they mimic black holes. An example is like boson stars or whatever, right? And those are, again, if we find them, of course, if we can prove that's what we are seeing, it will be, another Nobel Prize worthy discovery, right? But we have no evidence that they exist in any other way, like electromagnetically or something like that. Theoretically, we could distinguish between black holes and other exotic objects by looking at how the gravitational wave evolves right after the collision, but unfortunately our sensitivity is not good enough yet to resolve these minute features to a level of detail which is sufficient enough. So, putting together especially what I know for sure can happen from astrophysics, the most likely outcome is that it is, black holes that we're seeing.
Right. So, okay, and then it sounds like what you will learn by this, a little bit surprising then, find that the masses were a bit higher than what one would expect, maybe, is something more about the life evolution of stars.
Yes, absolutely.
And talking about that, there was an event in 2017 which was very, very important in terms of learning more about what happens with stars, not black holes. Can you describe what that was?
Yes, absolutely. So that was the collision of two neutron stars that we detected in August of 2017. I was also in Europe for the one. Somehow, during the first few discoveries, I was always in Europe.
There's a correlation here.
Well, yeah, exactly. I'll tell you about some jokes that my colleague told me. You should travel more often. Just go right at the beginning. Anyhow, so that was very different from the first one because now we are talking of neutron stars, not black holes. And now what is the big difference is that neutron stars are made of stuff, right? While black holes are made of pure gravity. So nothing can leave us a black hole as we know classically. Instead, if you take two neutron stars, which are two objects of the size, of Cambridge, since we are here, and but 1.5 times the mass of our sun, right? If you smash them together at half of the speed of light, then fireworks are going to happen, right? Because the material will start, being torn apart and flying around, right? And so one of the predictions that actually was made already prior to the discovery of gravitational wave from this system is that if you smash two neutron stars together, they should produce a lot of light at various frequencies. One would be what we call gamma rays. So it's a very energetic flash of light that actually were discovered, many decades already ago with light, of course, with gamma ray detectors flying around the Earth. And it was long theorized that the source of these gamma rays were the collisions of two neutron stars. And in 2017, we finally showed that is indeed the case. Then on top of that, you have this immediate flash of light, which is the gamma ray, but later you can have other types of light, which we call kilonovae, and that is basically really due to nuclear physics, because as the name suggests, neutron stars are mainly made of neutrons, right? And so after the collision, you have a lot of neutrons flying around, and they can enrich the material around it, basically bringing it higher and higher in the nuclear table, and then eventually these things have to decay like back pretty much, and that nuclear decays produce, of course, among other things, light, right? And because of the different time scale of different nuclear elements, this thing takes, a few hours to days until it finally kind of dies off. And then in even longer time scale, you have like radio emission. It's really a firework everywhere.
So it becomes like an intense nuclear laboratory far out there in space.
Exactly. Yeah. And so that's one of the reasons why this discovery was particularly exciting, because of course it brought together different scientific communities, right? It was people like me who are mainly interested in working on the gravitational wave side, but then you also people who work on nuclear physics, or people who work on supernovae, right, which is its own line of research. And it was at that time, I think this event was one of the events where most telescopes in the history of humanity were like pointed at the same spot of the sky, right? And it generated, of course, a huge amount of research, right? Because again, it's a treasure trove. It was the first time in the history of humanity that you saw light and gravitational waves from the same source, right? And so, for example, among the things that were learned from that particular source alone, as I mentioned, was finally the proof that binary neutron stars are the origin of at least some of the gamma ray bursts, maybe all of them, but also that they can produce these nuclear processes called kilonovae, which are were suggested and now we believe are actually the way in which you can produce most of the heavy metals in the universe, like gold and platinum and all the lower part of the periodic table through this like nuclear enrichment, right? And previously people believe you would do that in supernova during the supernova explosion, but it turns out it's actually much more efficient to do that with neutron star binaries. And on top of that, we could also try to understand with this source a bit better how neutron stars are, what are they made of inside? Because we say neutron stars, okay, and that it's roughly true. We expect them to be mostly made of neutrons, but nobody really knows, because the truth is that the density reached inside neutron stars is so high that A, we don't quite know how matter behaves in those regimes, and B, we cannot reproduce those regimes in a laboratory here at Earth. We just don't have enough energy to produce those conditions, right? So it's really a nuclear laboratory out in space. And so one of the things that we don't know then, it's exactly the content, if you go all the way to the core of a neutron star. And also we don't know, it seems very silly, how easy it is to squeeze a neutron star. Like we don't know if they're very like soft or if they're very, very spherical, you're never going to be able to squeeze them. And gravitational waves can tell us that, because if you have two neutron stars, it's just gravity, each of them is going to pull the other, right? And so if you are very, very easy to squeeze, then instead of a sphere, they will become like, oblate baseball balloons, right? And gravitational waves would tell us that. And similarly, light would also tell us something about that, because if it's very, very easy to break a neutron star, then you get a different amount of light from it, right? Than if it's very, very hard instead. Because if it's very hard, maybe we'll all fall in the black hole that forms after the collision instead of being like around. And so then this discovery allowed us to put some constraints on, technically it's called the equational state of neutron star, which is really what tells us how easy it is to, how soft neutron stars are.
It's just an amazing story. So this is called multi-messenger astronomy. I mean, this was really, is it correct to say it was the birth of multi-messenger astronomy?
It depends on how you count, right? Because I think formally speaking, you can also have, light and neutrinos are not light. So that also could be, depending on who you talk to, multi-messenger astronomy. Certainly the first one with light and gravitational waves.
Yeah. So I really hope if some physics or astronomy students listen to this, that they hear like what an exciting field that is, to combine gravitational wave measurements with these electromagnetic measurements from these colliding neutron stars. And talking about that, what we can learn from the future, we're going to wrap up soon. So you said we have LIGO now, we have Virgo, Carga, and they are upgraded. So, but looking on the timeline of maybe 1 or 2 or even 3 decades,
when your listeners will be professors and they want to know what they should do in the future.
Exactly. Yeah, yes.
Absolutely. Right. So actually, before I do that, just for completeness, I should also say that one of the things that we have done with the neutron star, which I think is very exciting, is to measure the expansion rate of the universe, like the Hubble constant. Okay. I don't know how much time we have. I'm happy to go back to this later if you want. Right. So let's see. So we detected the first gravitational wave in 2015. Since we have been operating in a regime where we have collected data, say, for a few months or a year, and then the detectors were turned off, and our friends that work with the instruments would then use the following months or year to improve some of the things, and then we restart with a sensitivity which is better, right, than before. And so that's the way we are operating even now. We are in the break between two observing runs. The last one ended in 2020, a bit earlier because of COVID. And after we were supposed to restart earlier than now, but after COVID, it was harder to do anything, like even just getting the parts, the hardware that you need, right?
So COVID also took a toll on the gravitational wave community.
Absolutely. Yeah. I mean, absolutely. Of course, compared with everything else bad that happened, this is a small thing, but we did finish a few months earlier because of COVID, and we restarted much later because of COVID. Right. So now then you can ask me, okay, great, Salvo. So I can keep doing this, and LIGO and Virgo will get better and better, right? And so where does this end? Well, actually, it doesn't end very far in the future, because it turns out that at some point, no matter how smart you are, how much you improve the polishing of your mirrors or the power of your laser, eventually you're just going to be limited by the fact that LIGO is 4 kilometers in size and Virgo is 3 kilometers in size, right? And a lot of our noise sources are just simply dependent on the length. So the longer something it is, a detector is, the better. Okay. And so what is going to happen in the next few years, say 5 years, is that our sensitivity will get better and better, because we're going to increase the power and change a few things, use quantum squeezing more efficiently, and so on and so forth. And so that will bring us from where we are now or in a couple of weeks, which would be a sensitivity such that we should get a new binary black hole merger every 2 or 3 days, something like that, and a neutron star every couple of weeks or something like this. Eventually, say in 2025 or 6, once we reach our design sensitivity, those things will get maybe a factor of 2 better. So we'll get a black hole every day, neutron stars every few days, right?
Black hole detection every day.
I know, right?
It sounds amazing.
we went in like 7 years from Nobel Prize party, first time ever, to, boring, another black hole. just like insane, just another black hole.
Yeah.
It was pretty.
Now it's every day.
It's pretty crazy, right? Yeah. And so eventually, though, we will reach a ceiling, right? We just cannot improve anything that will make a big difference, right? And now you may tell me, okay, Salvo, but that's fine. If you have a black hole every day and neutron star every couple of days, still seems pretty good. Like, so why don't we is the plan to just keep using LIGO and Virgo forever? And the answer is no, for a few reasons, right? So one of them is that if I keep running LIGO and Virgo as good and Kagra as good as they can be, they will detect a black hole every few days, but most of the signals will be very weak. Okay, they will not be super loud. And one reason why that's a bit suboptimal is that one of the things we want to do with gravitational waves is to actually be ungrateful to Einstein and check whether Einstein was right and general relativity actually works. Because there are good reasons based on quantum field theory and string theory to believe that maybe general relativity, it's an approximation to something else, right? And if general relativity breaks down, the place where it could break down is in a region where gravity is very extreme. What is more extreme than 2 black holes moving at the speed of light, right? And so one of the things that we are already doing, of course, but now it's very challenging because our signals are very weak, is to test whether the gravitational wave we see look exactly like Einstein predicted or whether there is something going on there, right? And in order for you to do so, convincingly, of course, you need something that is very clear, that really stands out of the data, and then you can check, does that look like Einstein told me it should look like? If it's very marginal, if it's very noisy, it's much harder, right? And so with the current generation of detectors, that's going to be very challenging. The other important limitation is that if you now think about where or when our sources were generated, they are pretty far, like for human perception of distances, a billion light years away, right? So a billion years ago. But in cosmological scale, they are in our backyard, really, right? And
so they're still not in our galaxy. It's in other galaxies, but they're still kind of local.
Yeah, so they're still like in a galaxy far, far away, right? to quote movies, but still, relatively speaking, they are nearby, right? Even once LIGO gets and Virgo as good as they can, a binary black hole like of 10 and 10 solar masses, which is roughly what I told you this maximum of the masses is, we would only be able to see that to a redshift of 1, which maybe doesn't mean a lot to many of your listeners, but is pretty nearby. To give you an idea, there is a lot of exciting science that can happen farther away. And I'll give you 3 concrete examples, right? The stars that we see here in our galaxies, or a redshift, this quantity dimension of 1, they are what astronomers call the population 1 stars, which are the most recently formed stars in the universe, right? But our understanding of the evolution of the universe tell us that if we go back in time, which means farther away from Earth, because cosmology is very puzzling, right, and confusing, there should be earlier generation of stars, right, that now don't exist anymore because they became supernovae, right? But if I look far enough in time, I should see them. Very confusingly, they're called population 3, even though they're the first.
Okay. Astronomers,
exactly, right? And now, we have never seen one of these population 3 stars with light. James Webb Telescope maybe find evidence for them, but they're not going to see one of them. They're just too far. They may just do an average something, right? But if those first generation of stars leave behind black holes in binary, then gravitational wave would see them, right? Unfortunately, if you go to our friends that do this simulation and ask them, okay, how far are these? They are much, much farther than LIGO and Virgo would ever be able to see them, right? I told you we can see things as far as redshift of 1. This thing would be a redshift of 12 when the universe was only a few hundred million years old, okay, as opposed to 13 billion years, right? And so that's one problem. The other thing is that if you go even farther from us, so earlier in the history of the universe, we mentioned this primordial black hole that may have been born right after the Big Bang. And I mentioned that then you would expect to find more of them the closer to the Big Bang you get. And LIGO and Virgo will never be able to see that far in the current facility, right? And so there are, of course, a gazillions of other reasons. But again, I want to impress the idea is that just running what we have now longer, it will give us more sources, but a bit more of the same. It will not open this different avenue to like the distance, direction. And so, because the limit is really the facility, then if you want to go past where we are or where we will be late in this decade, you need to build something new. And so what we are thinking about right now, both in Europe and in the US, is to build still interferometers, but bigger. So here in the US, we are working on a concept called the Cosmic Explorer, which is basically a scaled up version of LIGO. Instead of being 4 kilometers, it will be 40 kilometers, still L. And in Europe, they are also considering the option of building something which is triangular in shape for the reasons that I'm happy to talk about, but they're related to polarization information. And also to go underground, because in Europe it's much harder to find, 10 kilometers of free space on the surface, because it's just much more densely populated. And now, the rather, in my mind, insane thing about this is that these detectors would be the second generation of gravitational waves, right? Detectors. The third, because initial LIGO and Virgo in the early 2000s were the first. We are in the second. This will be the third generation. And if everything goes well with funding, we are thinking about the second part of the 2030s for operation. So it's not, forever away. It's 10 years in the future. And the rather, to me, a really crazy thing is that we would go from only one generation of detectors, from seeing the first gravitational wave ever in the history of humanity, to see basically all of the mergers of black holes everywhere in the universe. So to me, this is like if the person after Galileo built James Webb. Like, it's literally...
Yeah. That's a good example. I mean, I can't wrap my head around this, because it's even... To me, it feels like even like science fiction to say that what LIGO already has detected are black holes in other galaxies, nearby galaxies relatively, but still. Black holes in other galaxies merging, emitting gravitational waves that are detected on Earth. And now you're saying that in the 30s, end of the 30s, we can hopefully see all the gravitational waves emitted by the collision of black holes.
Absolutely. I think
it sounds...
I know. The way I like to put it is that with this next generation, we will basically run out of universe, because like we're going to see, because if you can see these objects far enough that there are not even stars anymore, then, you still may find surprises. Of course, that would be incredibly surprising, right? Like exciting. If you start, even actually today's, right, is one of the things that we hope to do, is to one day find something in the signal and you just don't know where it comes from, right? What generated it, right? The history of astronomy on the electromagnetic side, of course, has been full of surprises, of sources that nobody had imagined before, right? So, of course, we hope and expect the same thing to happen in gravitational waves. But even just with our, vanilla binaries, we will be able to see them in the 2030s, before when there were stars in the universe, which is really it is really something, right? It's very hard to, really also think about the time scale, right? Because it's like 10 years in the future. This goes really, really fast.
I'm in lack of words here. I don't know what to ask. Because it feels like science fiction, but it's only in 10, 15 years. 15 years maybe, there somewhere. So it's still very, very soon that we will be able to see this. So you mentioned cosmology now. We're talking about the entire universe. So I think we're going to do like this. We talked about so many things. So for the listener, there's so much to wrap their head around. So we're going to end now because you said also that we can use these mergers to do cosmology, even to learn something about the fundamental properties of the universe. So let's finish on that one.
Okay, absolutely.
Yeah, and wrap it up. Yeah.
So the idea, it's very simple, right? Astronomers have shown that the universe is expanding, and is even expanding in an accelerated fashion, so faster and faster, whatever that means in cosmology, which is not obvious. Now, how is that done? To show that something is receding from the Earth, okay, you need to measure two main quantities, its position and its velocity, right? And if you do things carefully, what you realize it boils down to, it's for a given, say, galaxy far away, to measure its distance from us, and a quantity that we call the redshift, which is related to the velocity that object has. And the way astronomers have historically measured the redshift, it's actually very, very straightforward and very well understood. The method relies on the fact that lights shine far away from us because they are burning hydrogen, right, and then helium, and then whatever. And nuclear physics tells us exactly what properties the light that is emitted in this situation should have, in particular the frequency of that light. Now, it turns out that if you take a source of light or a horn of an ambulance, right, the frequency that the waves are carrying away from the source will change if the source is moving relative to you, right? That's why police cars sounds different when they come and when they leave, right? And the same is true for stars. So if you know what the light frequency should have been, and you see that it's different when you measure with your telescope, that tells you how fast that galaxy is going away from you. Great. And that's very easy because we get light from stars all the time. But how do we get the distance? That is the problem, because light does not convey any information about the distance of a source. So the way astronomers have measured distances historically for the purpose of cosmology has been very, very challenging and complicated, and it relies on a multi-step process, which is called the cosmic distance ladder, because it's really in steps, where first you try to measure very well the distance of some stars in our galaxies. And those are variable stars, pretty much. And then from that, you try to find out one of these galaxies in another galaxy far away and relates the variation of its brightness with the distance. And you do this over and over, use supernovae. It works. And that's how they measure the expansion of the universe, Nobel Prizes, and so on and so forth. Why do gravitational waves help with this? They help because unlike light, which tells you everything you need to know about the redshift, but nothing you need to know about the distance, gravitational waves are exactly the opposite. They don't contain any information about the redshift in a way that you can extract, but they are simply related to the distance. The gravitational wave signal goes like 1 over the distance. So the farther away, the smaller it is. And so wouldn't it be great then if there were sources that emit both light and gravitational waves? Because then the gravitational waves would tell you the distance. The light will give you the redshift without any extra thing. You're done, right?
Complementary information.
And that's exactly what happened in 2017. And one of the reasons why this neutron star binary was exciting, because astronomers, our friend astronomers, did find the light from the galaxy that was the host of these mergers. And so from the light, they got the redshift, right? Gravitational waves told us that that object was a roughly 40 million parsec away from us, right? And from that information, we got a measurements of the Hubble constant, which is the local expansion rate of the universe, for the first time in a way that was nearly entirely independent from any of this cosmic distance ladder. And now the suboptimal thing is that the measurement was not great in terms of like uncertainty. It was pretty uncertain, right?
It's a first.
It was the first, right? Yeah. But again, the beautiful part of that is not, at least now, the fact that it's very precise, because it's not, but it's really the fact that it's independent from the other ways of doing this measurement. And I want to stress this because it may not be obvious to many of your listeners, is that right now we have two main ways of measuring this expansion parameter for the universe locally, and they disagree strongly, right? In fact, whole conferences in the last few years have been organized with titles like Crisis in Cosmology, and so it would be great to have a third way which does not share this potential systematic errors or cosmic distance ladder or whatever to arbitrate this tension. And that's what, at least potentially, we're not there yet, but in the next few years, gravitational waves can do for us.
So gravitational waves can help astronomers solve the Hubble tension then?
Pretty much.
Okay, that's amazing. And how the measured value that you got, how did that fare compared to the other?
Well, right now our uncertainty are, let me put it this way, our uncertainty are big enough that everyone still likes us because we still agree with everyone, right? Like we just span everything, right? Because our uncertainty are like 13.13%, and the uncertainty from these other measurements are like percent level. So like our error bars covers everything, right? That's why I said we're not there yet at the level to decide. And so, I cannot tell you we agree more with one side versus the other. It's a bit too early. It will take a few years, not decades. Again, it will take just a few years.
It's fantastic. So to summarize, I mean, it sounds like gravitational wave research from colliding black holes and neutron stars. It can help you analyze Einstein's theory, if that is right or wrong, when you go to very strong gravity regimes. It can help you understand the formation of stars and how they eventually die. It can help you solve the Hubble tension problem.
It can do more for us.
It's quite a lot.
we have not talked about it, and I don't want to drag this forever. But it turns out that gravitational waves can also be used to find dark matter in some cases for various reasons. At various level of exotic. You have people have proposed situation in which neutron stars will, after some time that they are born, will start to create that we start to form dark matter cores at their center, and then of course if they do, this like equational state I mentioned earlier, how squishy they are, will be different than if they're actually just made of normal matter. Another theory that I love because it's beautiful is that if dark matter is light enough, then you can show that dark matter particles will form clouds around black holes, the same way like electrons form clouds around the proton and the nucleus, right? And so these clouds of dark matter, which are called axions, very light dark matter, do to the black hole is that they suck energy from the black hole, okay? And they emit their own gravitational waves. Like now is the dark matter emits gravitational waves. And unlike the binaries, which last, is a gravitational wave that lasts a few seconds. We're not talking necessarily about duration, but these black holes are a few seconds, neutron stars a couple of minutes. These clouds could emit gravitational waves that last for years and years, right? And so, and I'm forgetting, I'm sure, hundreds of other things. We can find a gravitational wave from a supernovae, right? If we have an explosion in the galaxy of a supernovae, that will emit gravitational waves. And of course, it will be incredibly exciting. And we can also find gravitational wave from pulsars, right? Pulsars are rapidly rotating neutron stars. They're not in a binary necessarily. And it turns out that if a pulsar is not perfectly spherical, but has a small bump somewhere, then as it rotates very quickly, those emits gravitational wave at the same frequency, pretty much. Always it's monochromatic. We're looking for all of these things. We have not found them so far. So far, we have shown that pulsars are really, really spherical. And and if you have a mountain on a pulsar, it cannot be more than a millimeter or so in size, right? But we're looking for these things.
It's amazing. So I think it's quite clear that the message got across to, as I said before, if you have young students looking to a field to study, and there's a lot of exciting things going on, and most importantly, there's a lot of data coming in
Absolutely.
in the coming years. So we're going to wrap up there. Salvatore, thank you so much for talking about this, and good luck now with the future observation run.
Thank you.